Thank you.
Thank you, Stuart. And it's great to be back in Boulder. And as I mentioned in my introduction, I really appreciate this meeting. And one of the things I really like about it is all the early career people. I'm very late in my career. I have more ideas than I have time. So I'm hoping people will get interested in some of the problems I'm working on that I will not have time to finish. Um, so I'm going to present something, and it's kind of speculative, and it's actually a follow-on to what I presented here at my first in-person PCC 3 years ago. And this is about airburst chains, what we interpret as airburst chains. And I'm going to give two examples, but I'm going to focus primarily on the terrestrial one, the one that was found by my colleagues and their colleagues in the Atacama Desert in Chile. But there's also airburst chains, as you probably know, on Venus and perhaps on other planets. So my my co-authors are Pete Schultz of Brown and Scott Harris of University of Georgia, and they've done field work. They've gone there twice, and my first presentation in 2022 was just after they had published their first paper. It came out in late 21, and they've gone back since then. They had another field season in the summer of 23 where they found more evidence for airburst chains. But it appears that the new sites they found were very much off the track. So that kind of undermined the explanation I presented 3 years ago. And so we have to come up with another explanation. And I'm going to present one, but that's just kind of a working hypothesis. And so I'm going to start off. So Pete Schultz provided me with a lot of slides. So the first part of my talk is going to be his material. He presented this at LPSC last year in 24. And he gave me so many slides. I said, Pete, you couldn't have presented that in 10 minutes. And he said, I talk fast. Um, so on the left-hand side is a map and kind of an oblique view of the six sites they found, and their glass, what they interpret as an airburst glass, very much like the Libyan desert glass that we interpreted as an airburst form glass, a jet of very high temperature meteoritic material descends from the sky as the object that entered the atmosphere explodes. Its momentum carries it downwards, and it interacts with the surface and melts the surface. And that's how they interpret it. That's how I interpret it. I think that part of the story is correct. I discovered this paper about this uh, site on Venus, and let me click through Phoebe Reggio splotch chain. So it has 12 sites, and those are also interpreted as airbursts. They call them splotches, but they're probably formed by airbursts. And the center is radar dark, meaning it's very smooth, very fine grain, which could be glass, could be just very fine grain material. And then outside that, it's very rough. That is consistent with melting in the center and then a shock disruption from a very high pressure air shock in the outer ring. So this is Pete's content here, and I'm going to go through this really fast like he did, but my explanations probably won't be as good. So basically, it aligns with the Atacama Desert, these six sites that they found, and they interpret these as airbursts because the temperatures were too high. The melting could not be associated with normal natural fires. Of course, airbursts are natural phenomena, but they're very rare and they're extraterrestrial. But the heating and the melting happened at too high a temperature for them to be associated with just normal fires that would be grass fires or burning of plant life. So let's see here. Okay, so they were discovered actually by the colleagues of my colleagues, and several years before, way back in 2012. When Pete and Scott got involved, they started looking at the mineralogy, and one of the ways they determined the high temperatures, other than the melt and the quenching the glass, was the decomposition of zircon. So the zircons actually decompose at a temperature of something like 1700 degrees C, decompose into the component oxides. And that just can't happen at lower temperature. The image at the bottom, that's looking at one of their 6 airburst sites, or one of their 6 glass sites. And that's looking to kind of towards it's towards the Andes, looking to the southeast. And one of the things they noted was that most of the glass that they find is on the southern slopes, which kind of indicates the direction of the descent of this high temperature jet. Um, so um, there's more images on the bottom. So the upper right is the zircon, the thermally decomposed zircons. So this is kind of more of a close up. So these are the 6 sites with a distance scale. They actually span about 75 kilometers in distance, and the general trend is north to south. They don't all perfectly align along an axis. Some of them are a little bit to the east and west of the center line. So the field effort for the 2023, when they returned, they went around, all over the Atacama Desert looking for other sites, and they actually found some that were off site, and they haven't provided coordinates for those because they're worried that somebody's going to go there and pick them over. And that's happened with the Libyan desert glass in the western desert of Egypt. I mean, you can still go out there and find Libyan desert glass, but it's so picked over, most of the good stuff has been taken. And they're a little bit worried that, if they provide specific coordinates, that, people are going to go there and take it and put it on eBay or whatever. Um, so, um, so anyway, they have, done a lot of research. They're geologists, so they've looked at the sedimentary setting, and done a lot of mapping, and also taken samples back to the lab. They've determined the ages, or at least they have constraints on the ages. When they originally published their paper in 2021, they estimated it was between 10,500 years old and 12,300 years old. Unfortunately, that was misrepresented by the group that believes that there was this big Younger Dryas boundary impact. That would have been 12.9 thousand years. So that was already way outside the range. Their latest evidence suggests that it's younger than 11,500 years. And they've actually got material that they're doing more dating. So Pete thinks it's probably significantly younger than that. So anyway, on the right-hand side is kind of the impact ellipse, an ellipse that contains all the glass fields that they've found so far. It's still about 75 kilometers long, but now it's much wider. And that is the issue for the interpretation I presented 3 years ago. So what I proposed was that it was a very shallow, oblique impact, and it started fragmenting in the upper atmosphere, and then it fragmented into pieces of different sizes. So the bigger pieces continued downrange. The smaller pieces dropped out earlier and exploded before they hit the ground. And that is one way you could get a long chain. And that appeared at the time to be the most probable. But because now they found glass fields that are significantly displaced laterally from that ground track, we can't figure out a physical mechanism by which objects can be accelerated laterally. It's really hard to do because if it's coming in at greater than escape velocity, which it has to be doing, 11 kilometers per second, you can calculate what the lateral velocity would have to be to give it significantly displaced laterally by the time it hits the ground. That's a very high velocity. It's really hard to get those kinds of lateral accelerations. So let's see. I'm going to skip over some of this. These are the very visual. This is the very visual evidence. So I already mentioned we know there are high temperatures associated with it because of the decomposition reaction. There's also evidence that the temperatures are very heterogeneous and very rapid. So there are zircons that are perfectly fine, crystals of zircon, right next to decomposed zircon, which means there's very steep temperature gradients. And you cannot sustain a steep temperature gradient in a fire or anything, any slow process. It's got to be a very rapid process. This is the only mechanism we can think of, one, to get those temperatures, and two, to get those kind of gradients. And also they're very rapidly quenched. You can't quench rapidly without a steep temperature gradient. And that also implies that it's very transient. So there's also these morphologies, and a lot of these are Pete and Scott's interpretations. Pete, the third one from the top here, the spires. Pete interprets those as when the material was still molten, or at least in a plastic state, it also suffered rapid acceleration and percussion, and it kind of splashed up and it quenched while it was splashing. And there's a lot of evidence for this type of behavior. They exhibit a lot of folding. These pieces of glass exhibit folding, high shear rates, and even kind of like bouncing and sliding evidence that shows up in the texture. The blebs are little specks, like droplets that have recoagulated and then quenched. So there's all sorts of different glass morphologies. There's actually imprints of the existing flora. So as if a piece of molten or semi-molten material landed on, the ground, and there was vegetation on the ground, left its imprint, and then it quenched. I'm going to skip over some of this and just show the pictures. Here's some other evidence. Pete calls this dynamic emplacement. There's evidence that these things splatted, bounced, rolled, and so forth. A lot of it's, there's twisted morphologies, folded morphologies, and splashed. There's rings, and there, he has some close-ups of the ring morphology, almost as if it was a mud pie that hit the ground at high speed and then splashed radially. Here's one of these folded morphologies flipped over. You can see what looks like what was in contact with the surface alluvium, and then it flipped over. I think he's got, let's see. Yeah, there's these kind of circular features, and he's put these dashed lines to sort of guide the eye to see where it looks like something hit the ground and splashed radially. There's some here. Yeah, so some of them he can, tell the difference between an upper surface and a lower surface. The point is, this is very dynamic emplacement. It happened fast. It wasn't that's inconsistent with a vegetation fire. Let's see, let's go through here. This is the one that he compared to the splattering, the landing of a mud pie. So it was maybe starting to solidify, but it was still in a plastic state, semi molten when it landed, and then it splattered radially, and then it quenched. Let's see. Yeah, here's so the solid line in the lower right is basically the way he interprets it. This is the point of impact, and then there's radial transport, and then there's sliding across the surface, and then there are these rings, and he's found a lot of these. In fact, there's one even way off in the upper left is the edge of a ring, circular ring. Um, let's see here. These are what he interprets as flow features. So there's sliding, the center, the yellow arrows show the direction of sliding, and then there's this radial sliding across, and as it's sliding, it's getting more rigid. So the rheology is changing with time, indicating a highly dynamic flow. Uh, more of these type flow features. Also, yeah, they look at these they see shear layers in the soil. So again, implying this high velocity dynamic, but very transient flow. Okay, let's see. Let's skip through this because I'm going longer than Pete did in his LPSC talk. There's also this.
It's okay.
I'm sorry.
You have a half hour.
I have a half hour, but I got to talk about my stuff. So this is more decomposed zircon. So yeah, this is a big circle here. He's got the dashed line there. So you can see again, the way he interprets it is something landed, splatted, and expanded radially, and you get these kind of ring features. So he thinks, Pete does, and Scott think that the objects that created the airbursts came on an oblique trajectory from the south, because virtually all the glass you can find when there is topography, it's on the south facing slopes of the topographic highs. And so, a lot of these, I think the top one is looking to the north on a south facing ridge. And so they're all consistent. I think I showed the one in the lower right earlier, looking to the southeast. Oh, this is the one looking to the southeast, towards the Andes. And this work is from his Chilean colleagues who are sedimentologists, and the way they interpret it, and they see distinct layering of surge deposits, flow deposits, and an airfall on top of that. One of their colleagues is a volcanologist, and he's seen this type of stratigraphy associated with explosive volcanic eruptions, but explosive volcanic eruptions don't do this other stuff, and they don't attain those types of temperatures. Now Pete has compared this to other splotches on Venus, and I'm showing these on the right-hand side. And in this case, the surface of Venus, and these are radar images. So the radar dark is very smooth, probably glass or very fine grained material. The radar bright is very rough material, and there even appears to be what Pete interprets as like a mock from a bow shock, from an object coming in from a lower left, and it actually created a rough area. And it's actually somewhat consistent with the tree fall pattern at Tunguska. In the center there, where you see the movie, you can see an oblique impact. And this is one of my models. So the object comes in from the upper right, descends, vaporizes while it's descending. So the bright colors, the sort of fiery colors, those are indicators of high temperature. The cyan color, those are indicators of the shock wave. It's basically the kinetic energy density of the air that I'm showing there to show where the cold shock is. It's not high temperature shock, it's a cold shock that propagates across the surface. That would be roughening the surface. But anything at the bottom of where the high temperature fire colors show, that would be very high temperature. That would generate melt. That would look, whatever you end up with there would be radar dark on Venus. So this was his original, on the right-hand side, this was the original map, the original envelope, very long, very narrow. And here's the new map. That in circles, that's basically the boundary that encircles all these different glass fields that he's found. It's too wide, in my opinion, to explain by my previous explanation. These are just the guys in the field. Scott has done a lot of electron microscopy, Scott Harris. And so now I'm going to go back to what I presented here 3 years ago. So this is just a snapshot of that same oblique impact simulation. And so to refresh your memory, so the upper sequence is just a series of frames from an animation. So the early time off to the left, you see the object coming down. It hasn't hit the surface yet, but it's ablating, and all that ablated material maintains its momentum. It's very high temperature, and it keeps going down. It hits the surface, and it maintains contact with the surface for a significant amount of time. But to get multiple glass fields, you need to break it up. If it's a single object and it breaks up in the upper atmosphere, and then the big ones go farther, the small ones drop out earlier. And oops, let's see, I think there should be a video. Yeah, this is the video. And you may recall, those of you who were here 3 years ago may remember this. So they're all coming down and interacting with the surface and then rising buoyantly. And this is a map. So there's actually two plots here. We're looking down at the surface where I show the dark splotches. We're looking down. So the horizontal axis is the same for both, but the vertical axis is different. And then for the cascading fragmentation, I just show fragmentation points, solid lines for the first two, and then there's this kind of binary fragmentation sequence. Now, this isn't a unique solution. It is just, an example of a solution where you could get 6 airburst glass fields spread out along the track, similar to what I show here. This is just I showed this last time as well. The difference between a nuclear explosion, a nuclear airburst, or a static airburst, where nothing hot touches the surface. But if you maintain the momentum, if you put in velocity and it's got momentum, it goes down to the surface and you get this interaction with the surface. And then there's really 2 types of airbursts. One is the Tunguska type on the left. I've called that fire in the sky. It explodes. You do get a very hot fireball, but it doesn't make contact with the surface. The one on the right, which we associate with the Libyan desert glass, interacts with the surface, and that's what we think happened in the Atacama Desert. And it's the creme brulee effect. Basically, it's like a blowtorch. I'm not going to go through all this. This I showed last time. This was the summary that I presented 3 years ago. And I did say that. And then I added the revised hypothesis, which is something that I'm hoping everyone here can think about, because this is not the only possible answer. This is just the revised hypothesis. And so, you can think of, remember earlier this year, there's 2024 YR4, which was in an elliptical orbit, roughly in a 4-year resonance. So it's going to come back. We can't see it anymore. It's too far away. It's too small. It's going to come back in 2028. we're going to be able to see it again. And then it's going to come back again in 2032, and it still has about a 4% chance of hitting the moon. And some of us are rooting for that, I think. This is the risk corridor from that 2024 YR4. If it had hit the Earth, it would have hit one of these points. And this is interesting. It's interesting to note that the risk corridor is long and linear. And that is because if there's uncertainty in the position in its orbit, the uncertainty increases with time along the direction of the orbit. It doesn't increase laterally. So the same is true if you break something that gets within the Roche limit, it's got a distribution of velocities, but those are amplified along the orbit, not laterally. So again, if that chain of broken cometary or asteroid pieces hit the Earth, they're going to hit in a line, and they're going to create a chain. So one of the questions is, if there's a period of a year or longer of the fragments of something that's passed through the Roche limit, it's going to spread out. It's going to, be spreading at centimeters per second, but after a few years, it's going to be longer than the diameter of the Earth. Why don't we see these elsewhere? Well, this is just a notional thing. It's contrived to be consistent with the data, but you have to explain, why don't we see these impact scars, these airburst scars elsewhere on Earth? And it may be because the other pieces landed in the ocean, and the only place that they had preserved scars were in the Atacama Desert. There's another, explanation, and it's like the Atacama Desert is the driest place on the planet. Stuff isn't weathering, chemically weathering as fast there. If this glass was, say, in the Amazon jungle, you probably wouldn't find it. It would probably have weathered away by now. So this is just an evolution. Oops, sorry. Oh, there we go. This is an evolution of the string of the uncertainty in the locations of the virtual asteroids 2024 YR4, which explains why the probability went up. The estimated probability went up before the uncertainty ellipse got smaller and went off the surface of the Earth. Think of this now, play it backwards. That would be the locations of actual pieces of an object disrupted, if something passed through the Roche limit. And I'm going to finish up here, and I think actually this is my last slide. This is the impact corridor on the moon for 2024 YR4. If it hits the moon, it's going to hit somewhere along this line. But again, going from the virtual asteroids associated with 2024 YR4, think of this as actual fragments of an asteroid. So you can think of a crater chain across the moon, and if this mechanism is true, you might be getting very sparse crater chains that cover an entire hemisphere of the moon that have not been recognized yet. And that might be something you would be interested in, seeing if there is any evidence of craters that are of the same age that lie across, a linear trace on the lunar surface. And I'll finish there. And I'm sorry I didn't leave a lot of time for questions, but you can ask me during.
I was going to say we do have a minute, but my watch just ticked over. Are there any really fast questions? Amanda?
Anyone done textural analysis like SEM or EBSD on this material and compared it to tektites?
Can you repeat that? Because I didn't bring my hearing aids. And
Amanda will come up here and repeat it.
Okay.
I don't think I could do it justice.
Okay.
But I'm going to go ahead and switch it out.
Okay.
Hello. No. Yes. Okay. Can you hear me now?
Yeah.
Okay, great. Has anyone done SEM or EBSD textural analysis on this material and compared it to tektites?
I can't really address that. That was the Scott Harris part of this project, but I will be happy to put you in contact with Scott.
You.